We will now discuss the solution of a problem from the section Real Analysis, and the problem is related to the concepts of metric spaces. This question has appeared in the CSIR National Eligibility Test held on 16th September 2022, and it is a multiple select question, and it is from the part C carrying 4.75 marks. The given question is, let x, d be a finite non-singleton metric space. Which of the following statements are true? We are given four options. Option 1. There exists a subset A of X such that A is not open in X. Option 2. X is compact. Option 3. X is not connected. Option 4. There exists a function f from X to R such that f is not continuous. So we are given a metric space x comma d, and x is finite, and it is non-singleton. That means x is, the order of x must be greater than 1. Then which of the following statements are true? We will now discuss the solution of this problem in detail. We have xd is a finite non-singleton metric space. It is a metric space, and where the order of x is finite means order of x is finite, and it is non-singleton means order of x must be greater than 1. With this given hypothesis, we have to discuss the options given in option 1 to 4. So the first option is this one. We'll discuss about this in the next slide. We have the option 1. There exists a subset A of X such that A is not open in X. Now we claim that every subset of X is open. And the proof is, let capital A be any subset of X. If capital A is empty, then it is open. Why? Because in any metric space x comma d, the whole X, both capital X and the empty set are open sets. Therefore, if A is empty, A is open. Now let A be any non-empty subset of X. Agreed? Let the lowercase a be any element of A. We will now show that this small a is an interior point of A. For that, let R be the minimum of all distances from every pair of elements of capital X, and the elements should be distinct. That is the minimum of the distance of x comma y, where x comma y belongs to capital X, x not equal to y. That means you are measuring all possible distances between every pair of elements and taking the minimum of all those distances and call it as R. Now n, the neighborhood with center A and the radius R, is equal to the set of all x belongs to X such that the distance between X to A is less than R. Agreed? Agreed. If you take an element X distinct from A, then the distance between X to A must be greater than R, because R is the minimum distance. So if x is a, then the distance between a to a is 0, which is 0 less than r is greater than 0. It works. Therefore, this works only for x is equal to a. Thus, we will get the singleton a, which is contained in a. So, thus, we have a neighborhood with center a and radius r, which is entirely contained in a. This means to say that a is an interior point of the set A. Because A is chosen to be arbitrarily, this is true for every element of A. Therefore, every point of A is an interior point of A. If every point of A is an interior point of A, then A is open. A is open. So, and how A is taken? A is any subset of X. That means it's arbitrarily taken. That means every subset of X is open. So there exists, let's get into the option 1. There exists a subset A of X such that A is not open in X, but we have proved that every subset of X is open. Therefore, the option 1 is not true. We move on to the next option, option 2. Option 2, it is given X is compact. And yes, X is compact. Why? Because X is finite and X has more than one element. So X is finite, that is sufficient for us. So X is compact. Why? Because X is finite and every finite subset of any metric space is compact. Therefore, X is compact. So, the option 2 is true. We move on to the next option, option 3. X is not connected. Not connected. Yes, this is true. How? We will show like this. Let X be an element of capital X. Then the singleton X is an open subset of X. Why? Because every subset of X is open. Therefore, this is open. And the singleton X complement, that is capital X minus the singleton X. This is also a subset of X. Therefore, it's open. So, the singleton X and the singleton set, the singleton X and the singleton X complement, that is X minus the singleton set X. These two are open subsets of X because they are subsets of X and every subset of X is open. Agreed. Note that the singleton X complement is not empty because the order of X is greater than 1. Further, the singleton X, the singleton set X and its complement are disjoint. Yes. So thus, we got capital X is written as the singleton X union the singleton X complement. That is capital X is the disjoint union of two open sets. Disjoint union of two non-empty open sets. So that means these two, so they are separated sets. When you get a separated sets, that means this is what you are getting is a disjunction or disconnection. I'm sorry, not disjunction, it is disconnection. So we have separated sets, therefore X is disconnected. X is disconnected, that means X is not connected. Therefore, the option 3 is true. Okay, we move on to the last, fourth option. It says there exists a function f from x into the set of real numbers such that f is not continuous. Not continuous. We will prove that every function f from x into r is continuous. Let f be a function from x into r be any function. Any function. Now, for any subset G of R, consider F inverse G, that will be a subset of X. That is, F inverse G is a subset of X, and F inverse G is open in X. Why? Because every subset of X is open in X. So in particular, if G is a open subset of R, then F inverse G is also open in X. In particular, F inverse G is open in X for every open set G of R. So let's now recall one of the most famous theorems on continuity in metric spaces. A mapping F of a metric space capital X into a metric space capital Y is continuous on X if and only if F inverse G is open in X for every open set G in Y. So by this theorem, F, the function from X to R, is continuous, and F is any function. Therefore, this is true for every function. Therefore, every function F from X to R is continuous. So the option 4, that there exists a function f x to r such that f is not continuous, is not true, because every function f from x to r is continuous. Thus, the option 4 is not true. So the answer to this question is option 2 and option 3. So that is the detailed discussion of the solution of the problem from the section real analysis, which is related to the concepts of metric spaces. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.